In this section, we spent obviously some time talking about how heat transfers and so forth, but now we're going to apply that to a typical home. We look at older homes like we're going to be weatherizing, and we kind of analyze where these homes lose their heat. We're probably looking at about 25 to 30% of their heating and cooling costs are due just to air infiltration, air exfiltration out of the building. When we talk about air infiltration, what we're really referring to is air that tends to be blowing in through the wind through all the cracks and gaps. When we talk about other types of heat loss, for example, the roofs or attic area loses about 10 to 15%, about 20 to 25% through doors and windows, 20 to 25% through foundations, and 15 to 20% through walls. Now, every home is different. That's why it's important to recognize that these are not hard and fast numbers, but as a general rule, that's how the heat is lost and gained out of homes. Now, when we talk about air infiltration, it's essentially heat loss by convection. What happens is when wind blows on one side of the home, that puts that under a positive pressure. It pushes out the air you paid to heat and cool. So air infiltrates in one side, exfiltrates out the other side. So a good example or graphic of this is when we talk about wind pressure or wind, against essentially what's happening is air's blowing in one side of the structure, pushing out the air you paid to heat or cool out the other side. So we have air infiltration in one side of the structure and air exfiltration out the other side. Another mechanism for air infiltration or pressure differences in homes is what we call the stack effect. Warm air is more buoyant than cold air, so it tends to rise. Just like if you've ever held your hand in a fireplace, not with the fire operating, but you can feel a draft going up the chimney. That's because the warm air in the home is seeking a cooler environment. So that's what we call the stack effect. That's how attic ventilation works. In other words, we have air that goes in through the soffit vents. It gets heated in the attic, it rises, and then goes out through either the ridge vents or gable vents or pod vents at the top of the attic. But that's heat transfer by the stack effect. And then another mechanism that impacts heat transfer are mechanical systems. In other words, when we have fans in our blower motors and our furnaces, and we have our ductwork located outside of conditioned space, that can create pressure differences that cause air to infiltrate in. And we'll talk a little bit more about that later. But when we talk about air infiltration, this is really what we're seeing. It's just air coming in through all the cracks and gaps around penetrations, plumbing penetrations, leaks in the building envelope. Okay. One of the things that we do in weatherization programs is that we caulk and seal around penetrations for wires and plumbing. We put gaskets on outlets anywhere that there could be a potential hole in the envelope, which is our walls and our floors and our ceiling that separates conditioned from non-conditioned spaces. We try to seal those places up so that we can stop that unwanted air infiltration. When you look at weather stripping around a door, the reason that we weather strip is because oftentimes doors do not seal tightly, and so that becomes a very easy way for air to infiltrate into a home. When you look at this infrared image here, you can see that the white and the yellow areas around this door are leaking heat pretty well. So not a good thing. So we use weather stripping around doors and windows to reduce that heat transfer. Another important concept to understand for energy basics is this concept of what we call the thermal envelope. That's essentially where we're kind of defining the difference between indoors and outdoors, where we're kind of defining the difference between what we call conditioned space, where we have to condition the air, whether we have to heat it or air condition it, and the outdoor space, which is what we call unconditioned spaces. So for example here, when we look at our thermal envelope, we're seeing that our walls are insulated with this fiberglass insulation, the pink areas. We see that our floors are separated from the crawl space by floor insulation. Sometimes they insulate the perimeter of the foundation walls as well, or instead of the floor. And then we also have the insulation at our attic levels. But when we talk about a thermal envelope, this is a pretty good visual that kind of describes that. Now, when we look about what that looks like in the real world, oftentimes when insulation is installed, it's installed very poorly. Doesn't work well. For example, here you can see that the fiberglass insulation here is just crammed into this sloping roof, and it's not going to work very well because when the insulation is compressed, it loses some of its ability to trap air, so its R value drops and we don't get the performance. So when we talk about buildings looking good on paper, they may have R30 insulation, for example, like we have here in an attic area or sloping roof area, but it's not going to perform like that because it's compressed. Same thing happens with walls. You can see here the insulation is just crammed in between the studs instead of actually being cut and fitted into that opening. Again, these compressions have a big impact on the overall performance. It can reduce the performance anywhere between 30 and 50%. And then, of course, when we look at an infrared image of heat loss around the band joist area or at the bottom, just below the floor line, you can see here that these brightly colored areas of orange and white and yellow indicate a lot of heat loss. Typically, when we look at a band joist area, they just cram the insulation in these spaces, and it doesn't work very well. So it's important that the insulation be properly fit, cut into that opening so it can actually, and not be compressed, so that it actually works well. This is what a perfectly insulated wall looks like. The insulation is touching both the studs, the upper plate, and the lower plate. And so this wall is well insulated and it's going to perform well. And the people are going to be more comfortable as a result of the insulation being installed properly. There's other types of insulation that we use. For example, this is a person spraying spray foam. Spray foam insulation basically creates, thousands, if not millions, of little bubbles, per square foot that help trap air. So foam is probably one of the better insulators in terms of R value. We also have what we like blown-in cellulose, for example. When oftentimes we'll retrofit walls that have no insulation and we'll drill holes in them and then take much like a giant blower and have a tube, and we'll actually blow insulation into that wall cavity to fill it up with basically cellulose, which is chopped up or newspaper. Okay. Now, when you hear people talk about the dew point, what we're referring here is that, let's say it's 70 degrees inside and let's say it's 30 degrees outside. As the temperature, as we go through that wall, eventually the temperature starts to drop. And if we have moisture in that wall cavity, it actually can condense on cold surfaces. So some parts of the state or country can have cold enough temperatures where moisture vapor that comes in as a result of air exfiltration can actually condense and grow mold and so forth. So that's another reason that we seal up our wall cavities and do a good job of insulating them, is because we want to create those surfaces, we want to make them as warm as possible so there's less potential for condensation. So when we refer to a dew point, what we're talking about is the temperature at which the moisture in the air condenses. When you go outside, for example, on a cold day, you can see your breath. That's their warm, moist air in your breath actually reaching its dew point. When you see moisture condense on a warm summer day on a cold beverage can, that's because that can's at its dew point.